Okay.
Sure.
Good morning. How is volume level? Does that work? Yeah. Okay, great. Good morning. Thank you for being here. My name is Cory Myers. I'm a software engineer at the Freedom of the Press Foundation, and along with Felix Linker at ETH Zurich, we're excited to present a case study in the co-design and analysis of a secure protocol for whistleblower communications. And just for time, we'll take questions at the end. We're going to tell the story in two parts, starting with the motivation and design of SecureDrop as a system that currently exists, and then explain how it's evolving. SecureDrop is a whistleblower submission system that media organizations and NGOs can use to securely accept documents and messages from anonymous sources. It's been used by dozens of news organizations around the world since its inception. As an open source project, it was begun in 2013 by the late Aaron Swartz, and since then it's been stewarded and maintained by the Freedom of the Press Foundation. My colleagues Ro and Julio are also here today and have been driving a lot of this work over the past couple of years. SecureDrop's design is largely unchanged since 2013. We won't go into great detail of the current design, but the interesting thing to note here is that it is not end-to-end encrypted. Messages are encrypted in transit via Tor Onion services and on disk via OpenPGP. And the motivation for this design and the reason that we think this has been justifiable as an approach over the past decade is that really the fundamental goal of SecureDrop as a system is to raise the cost of compromising the server by moving the attack from one domain to another, from technical to physical security to legal compromise. The way we achieve that high cost of compromise is to require news organizations to host their secure drops on physical servers in locations they control. To just give a sort of straw man example of why that's useful, in the US, for example, it would be a big deal for the FBI, the Federal Bureau of Investigation, to raid the offices of the New York Times over a suspected leak case. They could do it, but it would be a big reputational risk. They'd have to justify it legally, and it would set off a legal battle. Although SecureDrop is open source and anyone can download the software and install it, we insist on this approach for any SecureDrop installation that we provide support to as a way of enforcing that escalation of cost. At the same time, we know that this requirement is a burden for many news organizations, and we want to broaden SecureDrop's accessibility. We want more journalists in more kinds of environments to be able to use SecureDrop to receive tips and documents securely. For example, what about news organizations that can't afford hardware or don't anymore, especially after the pandemic, have a physical office where they can install it? What about news organizations who don't have a Linux systems administrator to run 2 servers on a firewall? What about news organizations based in locations where this is actually the wrong threat model because physical security can't be counted on and legal protections don't exist in the way that SecureDrop was originally designed for in the US context? What about individual journalists who may be primarily publishing on Substack out of their home offices, but nonetheless are doing work on the national scene and want to be able to receive tips securely from anonymous sources? Our own research and lots of feedback over the years suggests that this accessibility goal really reduces to the question of how a news organization can ask a third party to host a secure drop for them. That might be in the cloud, it might still be physical servers, but in either case, it breaks our model, our assumption that you're running physical servers in an environment that you control. And the table stakes technical question there is how can SecureDrop be end-to-end encrypted? So we began thinking about this a few years ago and abstracted some requirements from how SecureDrop has actually been implemented and deployed over the past decade plus. A newsroom is going to run a server. It's going to enroll some number of journalists for whom this kind of reporting line is relevant to their work. The server will be accessible by Tor Onion services so that we inherit Tor's anonymity properties. Anonymous sources will connect to the server via Tor browser. They'll get a passphrase that is their only piece of state for that session. They'll send messages. In SecureDrop, it's currently deployed, and in future work, they'll be able to upload files. That's out of the scope of what we'll talk about today. And they can return to the server to reply to other messages they get back from journalists. The journalists who are enrolled then can log into the same server. They can retrieve messages. They can download files in current and in future work, and they can reply to messages. As we looked at these, we found that there were some implications from these requirements that were not immediately obvious. One is that we consider SecureDrop to be a solution to a kind of first contact problem between people who are highly visible and well known on the internet and want to be contacted, and anonymous parties. And that effectively means that all key distribution for this system has to be in-band. For journalists, that means that their keys are publicly available, and so sources download them and can encrypt messages to them. For sources, they actually enclose their keys in messages to journalists so that journalists can reply back directly to them. Sources have no persistent state between sessions. We'll come back to this. Each conversation is one-to-many between a source and however many journalists are enrolled at the time. Conversations can be highly asynchronous, and that means that we can't rely on any system that depends on participants being online at the same time, either for the initial bootstrapping and key agreement or for actually having a conversation. And we want to trust the server as little as possible. So we want to minimize the amount of metadata that the server holds at any given time apart from the messages themselves. Now, looking at these requirements, you might well ask, especially in this crowd, why we're not just using Signal or MLS. And we thought about this a lot. We actually did some prototyping work a few years ago to look at an implementation of the Signal protocol for this purpose. We consider it best-in-class secure messaging. Signal in particular is a staple of the recommendations that our colleagues on our digital security training team make to journalists about how to secure all the rest of their communications. And we knew that groups could accommodate one-to-many messaging from sources to journalists. What we found, though, was that a few of these requirements in particular wound up violating things that we needed. So for both Signal and MLS to do key ratcheting, you need some kind of app or session with persistent state to ratchet keys. And that violates our requirement that sources have no persistent state to actually run the protocol across sessions. The alternative to that, you can do something clever with opaque. You can encrypt your current session state and store it on the server. And that way the client doesn't have to store it. The client is still stateless, but then you've created very persistent evidence on the server of this session, whether or not there are messages associated with it. For Signal or MLS in large-scale deployment, this is a non-issue because if you're looking at millions of messages a day, having visible on the server session bundles doesn't mean anything. If you think about this as a very low volume, high stakes messaging service, where the presence of even one new, in this case, a source session bundle means that a new source is connected to the server, that's actually highly revealing metadata in its own right that we wanted to minimize. So we began looking at this again in about 2022. My colleague Julia was leading a lot of this work at the time. And began looking at what it would look like to do an end-to-end encrypted messaging protocol specifically to satisfy these requirements. In 2023, we had a first proof of concept that laid out some of these security requirements on this threat model, a first draft of the design, and an increasing wish to be able to do some kind of formal modeling to prove, given the stakes, that we were actually going to achieve the security properties we wanted. As luck would have it, we've been going to IETFs for a couple of years at that point. At 118 in Prague, Felix gave a workshop on the Tamarin security protocol verifier operating in the symbolic model, and Julia and I were there and thought it would be a pretty good fit for the kinds of analysis and modeling that we wanted to be able to do. So we attended the workshop and immediately found that as soon as we modeled the protocol, we couldn't get Tamarin to terminate. We knew immediately why, which is that the most novel part of this protocol relies on the commutativity of multi-party Diffie-Hellman key agreement, and that immediately led to a state space explosion in Tamarin that we couldn't manage, and it turned out in short order neither could Felix right away.
Yeah, and that's where ETH Zurich came in. So I must admit, I would have loved for Tamarin to work out of the box for the Freedom of the Press Foundation. But on the upside, that not being the case led to a great collaboration for us at ETH Zurich. So when the Freedom of the Press Foundation approached us, telling us, hey, we have something for you, they actually came quite well prepared. As Cory said, they already had security requirements, they had a threat model, they had a design, and certainly they had a strong desire for formal analysis. And this is what I'm going to talk about in the second half of this presentation, the formal analysis that we conducted of the SecureDrop protocol. So The work that we did as a team was really an iterative process of taking all these three inputs, the security requirements, threat model, and design, formalizing them both in the computational and in the symbolic model. So doing both pen and paper proofs, more on the cryptographic primitive side, and doing symbolic proofs using the Tamron prover more on the protocol level side. And out of those formalizations, we typically got output that suggested there is a room for improvement or maybe there is a flaw. We took those outputs and then informed a new iteration of the security requirements, threat model, and design, which we then again formalized in those two models. So in the rest of this talk, I would like to talk about all these aspects to finally give you a quick sketch, way too high level sketch of the properties that SecureDrop achieves. So SecureDrop was designed to provide 4 security requirements. Earlier, Cory already talked about the functional requirements that the system has. Now let's talk about security. So first, evidently, the messages exchanged over SecureDrop must remain secret. So SecureDrop has a requirement for confidentiality. Second, also quite clear, we have the requirement of anonymity. Sources using the system must remain anonymous when doing so. Then third, this is not such a common requirement. The clicker doesn't work. Oh, no, it works. Yeah, we have the requirement of undetectability, which means that messages should be not visible to the adversary in any way. They shouldn't be able to, for example, count messages. They shouldn't be able to see the timing of messages when they're exchanged. And finally, we have the requirement of authentication. Sources and journalists in their communication should be able to do so authentically, being assured who they're actually talking to. SecureDrop aims to provide the security requirements in a very complex threat model. For example, we consider that any of the parties using the protocol could become compromised during the protocol run. Sources could be compromised by, for example, leaking their passphrases, or it could be that an adversary simply mimics a source by connecting to the SecureDrop server themselves. The server is now hosted in the cloud, so compromise of it must be considered as well. And journalists could reveal their key material, which could lead to the adversary impersonating them. In particular, for the server, we would like to distinguish between active and passive compromise. Both scenarios are possible, but the passive case is much more likely, and we would like to understand exactly what happens in this scenario. And naturally, we're also concerned about adversaries that may obtain quantum computing capabilities in the future. It was clear to the Freedom of the Press Foundation from the beginning that a SecureDrop design will probably not be able to provide all these security requirements against all adversaries to the full extent. One outcome of the formal analysis is that it helped us to be precise which security guarantees precisely are guaranteed against which adversaries. But to understand that, you first need to understand how the SecureDrop protocol works. So now let's talk at a high level about how this works. So at its core, the SecureDrop protocol uses 2 cryptographic primitives. There are more, but I'm introducing these 2 now only. We use a standard public key encryption scheme, PKE, that just does public key encryption. And we use a second public key encryption scheme that is authenticated, and we abbreviated that with APKE. And authenticated means that you can verify which sender generated a ciphertext. We combine both these encryption schemes into a message encryption scheme, the ciphertexts of which are then exchanged over a message delivery protocol that runs over Tor. Let's take a look at some details. In the message encryption scheme, senders generate 2 ciphertexts. First, they use the standard public key encryption scheme to generate a metadata ciphertext. With that ciphertext, they encrypt the sender key. Second, they use the authenticated public key encryption scheme to encrypt the actual message they want to send to the recipient. The key for authentication of the APKE is the one they encrypted in the first ciphertext. They take both these ciphertexts and then want to evidently send these to the recipient. For that, they use the message delivery protocol. How does this work? On a high level, unfortunately, we have limited time. So in the message delivery protocol, the sender would like to send a ciphertext anonymously and undetectable to a recipient. They do so by uploading this ciphertext together with a clue to the server. The server simply stores the ciphertext and clue for later use. Recipients can contact the server and ask it whether there are any messages. When they do that, the server generates a challenge based on the clue, and if the recipient successfully solves that challenge, they are given the ciphertext. Critically, the clue reveals nothing about the recipient to the server, and the challenges are re-randomized with every request. This allows the message delivery protocol to provide both anonymity and undetectability in the two outsiders connecting to the server. Now let's talk about the formal analysis. In our work, we provide proof for all 4 security properties that SecureDrop provides. We provide proof for anonymity and undetectability in the computational model doing pen and paper proofs. For confidentiality and authentication, we split our work into primitive level proofs that are carried out in the computational model, doing again pen and paper proofs, and protocol level proofs that are carried out in the symbolic model using Tamrin. From the interactions of these two worlds, we took away that the computational model really helped us finding the best abstractions for the different building blocks that we use in the protocol, whereas the symbolic model using Tamrin helped us detect regressions in our iterative analysis loop. And Tamrin's support for machine check proofs really helped us there. What I find particularly neat is the handover that we do between the computational model and the symbolic model. And I'd like to give you an intuition for how we connect computational and symbolic proofs next. But before I go into that, a quick footnote. So I said we connect, there's a handover. The guarantees we have there are not formal. It's more a methodology of how to approach the verification. So let's take the authenticated public key encryption scheme as an example. Under the hood, this authenticated public key encryption scheme is using the HPKE RFC in the auth PSK mode. So we could reuse some guarantees, but we found that the proofs that have been done of this public key encryption scheme weren't quite there where we needed them. So Shannon, the lead cryptographer on our team, proved the 2 guarantees insider CCA and outsider authentication of this cryptographic primitive. The first guarantee intuitively means that the adversary cannot learn anything about messages being exchanged, about the contents of the messages being exchanged, and authentication means that it's hard for an adversary as the outsider to generate ciphertexts. In the symbolic model, what one would typically do is write equations that define how encryption and decryption operations interact in the symbolic model. These equations hold unconditionally and can be used always. We didn't follow this approach, but instead axiomatized the computational guarantees that were proven in the computational model. We write properties that relate decryption events to the structure of terms and other preconditions that are required. This approach was pioneered by Cas Kremers and his co-authors, for example, in papers like Keeping Up with the Camps. This axiomatization approach allows us to explicitly capture the assumptions that the computational guarantees of the cryptographic primitives rely on. If they hold, things go well and the protocol is secure. But if they don't hold, all bets are off and the adversary can, for example, choose the result of decryption events. The benefit of this axiomatization approach is that it provided us with a clear separation of concerns. Shannon, the cryptographer, could focus on the computational guarantees of the primitives, and I, together with Luca, could focus on the protocol level security guarantees in Tamrin, and we had a straightforward, not straightforward, but we had a clear methodology, a clear set of steps to take when deciding how we model the cryptographic primitives in Tamrin. And moreover, this is a more accurate model of the cryptography. Some findings that we, so these are some example findings that we got from during the security analysis. So with this methodology, we found an attack on the message delivery protocol during the design that was actually quite simple, but it went unnoticed for quite a while nonetheless. And in particular, the precise model of the cryptography in the symbolic model made us stop making claims on protocol level replay protection guarantees because the computational guarantees that Shannon proved on the primitive level weren't quite there to allow us to prove replay protection on the protocol level. But as a footnote, SecureDrop as a system overall will still give you replay protection, just not provably on the protocol level. With that, let me show you our results table and which security guarantees the protocol provides. So at the end of the formal analysis, we found that it's best to distinguish between these three adversaries for the security guarantees. We have an external adversary. This would be someone like you and me, simply connecting to the SecureDrop instance and doing whatever. We have a passive server adversary who, for example, obtains a disk snapshot of the server running in the cloud. And we have an active server adversary that, for example, could also deviate from the server message delivery protocol. You see here a couple of atom footnotes. This means that the security guarantees are degraded against the harvest now decrypt later adversary with post-quantum security, with quantum computing capabilities. So next, let me give you an intuition for why certain things do not hold. So for undetectability, we cannot provide this property against a malicious server because the server is given the ciphertext and stores them in the database. So this attack is quite straightforward. There we cannot provide this guarantee. For anonymity, an active server can identify the public key of a recipient by deviating from the message delivery protocol and doing some funky business there. And for the post-quantum security guarantees of undetectability and anonymity, the message delivery protocol is not post-quantum secure right now because it relies on the commutativity of elliptic curve Diffie-Hellman. So an external adversary in particular, for example, could regularly query the server and then find out which public key received messages at what times. Also, you see that we have all these green check marks for confidentiality against all adversaries here, and that is true, but this is actually way too simple than what the protocol provides. There are very subtle and different guarantees based on the parties. So there are different security guarantees for sources and journalists, and with different notions of forward secrecy and post-compromise security, both of which are provided by SecureDrop. But for details, find me in the hallway later. So we decided that it's best to have two sets of conclusions, one from the ETH Zurich and one from the Freedom of the Press Foundation side. And I would like to start with the ETH Zurich conclusions. I went into this project already believing that everyone should formally analyze their protocols. And it probably comes to you as no surprise that the collaboration, it was really fun, and I learned a lot to reinforce this belief. In particular, this was a learning for me. I saw in this particular case study how you really need both a computational and a symbolic analysis. And I think we provide a great case study for how to combine them practically. Also, as a footnote, let me say that many details of SecureDrop, the protocols, the security guarantees were not covered. So this is a formal invitation to nerd snipe me on the hallway. I cannot make this invitation on behalf of the Freedom of the Press Foundation, but maybe you do it.
Please do. Yeah, we really just wanted to model it in Xamarin, and that was 2 years ago now. It's been a great project. It's also been an enormous effort on all our parts to make this happen. But I think the benefits have been greater than we expected. We thought we were going to get proofs. We wound up getting this two-phase, two-mode set of proofs that I think have also let us iterate on the design faster because we've had the confidence of both ETH Zurich's expertise and these tools to sort of backstop decisions that we make both at the primitive level and at the protocol level. I think all I'll say, just to leave time for questions, is all of this sort of in parallel with the distinction between the symbolic and the computational proofs that Felix mentioned. We're assuming implementation with verified primitive libraries. We're looking at how to then couple our implementation with some kind of verification to the model as well. And so we want to reuse as much of this proving work as possible as we proceed towards implementation so that the implementation inherits the guarantees that we've been able to prove. Thanks.